Can you hear me still? Okay.
Yep.
Great. So our next speaker is Tomaz Prosen. Unfortunately, Tomaz was not able to join us in person, but we're still very happy to have him speaking on Zoom, and he's going to tell us about quantum many-body Ruelle resonances. So go ahead.
Thank you. Yeah. Sorry. Yeah. Apologize for not being able to attend this meeting in person, but still, I hope I can contribute a little bit to it. Yeah, I mean, the aim of my talk is to discuss the concept of many-body Ruelle resonances, which maybe is not yet a very familiar topic in many-body physics, even though it's been around for decades in mathematics of dynamical systems. But I feel like it's an interesting concept, and maybe we can discuss it a bit, in the context of thermalization. Second kind of what's going on? Yeah. Second kind of main aim of my talk is to introduce a simple, very simple class of models, which we call Floquet East quantum circuits, or Floquet East quantum circuits, which we all like kind of simple models, right? Which can be used for analytical and simple numerical calculations. And I would like to convince you in this presentation that these East circuits, as I will introduce in detail, are even though they are so simple models, they are probably exhibiting some interesting phenomena in the bridge between, let's say, localized and ergodic or thermalizing dynamics. Yeah. So I will discuss a couple of issues, and not only Ruelle-Pollicott resonances, but I will discuss discussing a simple what I would refer to as dynamic localization transition in this quantum East circuit, and yeah, and then I will go into towards the transition point, and beyond the transition point, let's say in the ergodic side of the presumable transition, and I will try to characterize ergodic side in terms of resonances, in terms of decay modes. I mean, just to break. I mean, to give you a bit of a spoiler of what is going to be about. I mean, the necessary ingredient of this concept is exponential decay of correlations. So I mean, as we all know, I mean, exponential decay of correlations are very common in many-body physics. And here the idea is to be able to describe the mode which dictates exponent, the leading exponent, asymptotic exponent of decay of correlations. And this can be related to some sort of eigenvector of some transfer matrix and the gap of the spectrum of those transfer matrix. And yeah, and the question is, can we describe it in some quasi-exact or simple terms? So this is a couple of papers that I'm going to discuss in my talk, but moreover, in the last part of my talk, actually, I discussed stuff which is not even published. I mean, it's not even written up, even though I kind of tried to convince myself to write it up for a couple of months now, but hopefully it will be done soon. But the model itself that I'm going to discuss has been proposed and discussed in this recent PRL with Bruno Bertini and Pavel Kos. There we discussed this dynamical localization transition, which is a very simple effect, as you will see. But the dynamical decay modes, I mean, the chaotic decay modes have been, this kind of concept has been proposed many years ago in these papers of mine, in particular in first time in this JPhys in 2002. And I mean, this is kind of interesting, when you get old enough, I mean, then you start to, remember some results that, you got very excited about, but nobody cared. And this is one of those results where I really kind of enjoyed it. I mean, I really thought, okay, this is something, but, nobody cared. I spoke about this at a couple of conferences. Nobody asked questions. Nobody understood what I wanted to say. And well, I mean, then until very recently, Takashi Mori came up with this paper, and I got excited. Wow, people started to care. So And then Marko Žnidarić, a colleague in our department, also wrote a paper recently on momentum resolved Ruelle-Pollicott resonances and so on. So yeah, so I mean, it's always nice, you know, to get people interested, right? Even though, so I think, I hope now this concept will kind of get revived, and maybe, you know, we'll get somehow deeper into it. I mean, also I want to kind of disappoint you. I mean, we don't know much about this. I mean, this is just a concept which, as I say, has been quite developed in mathematics, in few body dynamical systems, but in terms of many body physics, we don't even, I mean, I'm not even sure if you know the correct mathematical tools to describe it. I mean, so basically what I'm going to speak about will be some numerical experiments, you know, some proposals and some numerical experiments, which kind of seem to be quite suggestive. Okay, so, and please, of course, you stop me whenever there is a question or something unclear. It's kind of hard to give a Zoom talk without having a clear faces of people, even though I see the room, but still, I mean. Okay, so let me just introduce this kind of class of models, which I claim. Okay, so I maybe go back for a slide. You know, in this kind of first papers where I discussed this concept, this was discussed in the context of this kick-teasing model, which also now has been quite popular in the literature, but it turns out that the kick-teasing model, I mean, the reason why I proposed it more than 20 years ago was that it was extremely suitable for discussing finite time dynamics in quasi-exact way, right? Because there was, there was no approximations, right? The model is a circuit or a Floquet system, and you can describe Heisenberg dynamics of observables without approximations for finite time. So you can define some sort of temporal transfer operator, you know, just composing time evolution with some sort of noise, some sort of coarse graining. And in this way, you get a closed system, closed dynamical system. And so what I want to say is that, you know, kick-teasing models seem to be an ideal test bed for that. But what I want to claim now is that, you know, East circuits are maybe even better. I mean, in the sense that they are even simpler, that they don't have some conceptual difficulties that you encounter in kick-teasing model when you look at translation invariant observables. In any case, so let's just get onto this story. So what I have in mind by thinking of chiral circuits or East circuits is a conditional, it's a brickwork space-time fabric. But rather than using the standard brickwork, I take a conditional gate where the left qubit is just a spectator and the action is only going on the right qubit. So it's this kind of, I mean, I'm not sure if this is the most standard notation, but I hope it's clear. For me, time always goes bottom up. I mean, it's always vertical. And this just means that, you know, this gate, this is a unitary gate, which is conditioned on the state of the left qubit. Yeah? So for example, if the left qubit is in state 0, then you do nothing, right, on the right. If the left qubit is in state 1, then you do something on the right, okay? And as a simple example, and this is something that actually has been picked up from what people have discussed before, I mean, from the so-called Hamiltonian East model. For example, what you can do is you can take this conditional flip. So you take X gate with the amplitude A, and you subtract 1 in order to make it, well, I mean, in order to make it a stochastic matrix if time is imaginary. But suppose time is real, right? So then you just take a conditional X gate, right? So you just, if you want to write it as 2-qubit gate, then you take a projector. This P is just a projector on the speed 1 state. And if the left qubit is in spin 1, then you take a conditional rotation, right? Okay, so it's really the simplest thing you can imagine. But of course, most of stuff that I'm going to speak about will be true also for any kind of single qubit gate, which is written here in pink. Okay, so now what you can imagine now is an infinite, I mean, this is defined on an infinite Z, but imagine now that you have some special boundary condition where everything to the left of something is in the state 0. And then there is some impurity, which is in state 1. And then there is again something to the right. I mean, everything to the right of 1 is still in state 0. So then things can start happening, right? Because if there is, sorry, I don't see my, no, sorry, I was, yeah, I think it's fine. Okay. Anyway, so what I want to say is, yes, if you start with all zeros, of course, nothing happens, right? So you need an excitation. And when you have an excitation, then information starts to propagate from to the east, right? That's why it's called east model. So things start to get propagated to the east. And if you start from state zero, then of course, from the property of this gate, then you can simplify. For example, you want to compute the state after t time steps. Now, again, my time steps are in this. I consider this circuit as diagonal layers, right? So this will be my single time layer. But of course, if you start from state 0, 0, 0, right, then of course you can simplify that. So at the end of the day, you have to basically compute this kind of partition function on this triangular lattice, right? So everything here is in state 0. Here is an arbitrary. So basically, this is the way how you compute the state, right? You start from state 0 and you apply this triangular circuit, right? Now, the question is, I mean, is this easy or is it hard? I mean, we don't know. But I try to convince you that there is an interesting potential transition, right? Depending on the flip rate or flip amplitude A, things can dramatically change. And of course, this has been known. I mean, at least, I mean, in a special context, let's say of Hamiltonian East, this kind of transition has been suggested before. It was actually in this first paper in 2015 by Juan Pigarajan and collaborators, where they basically imported this problem from the classical glass physics. I mean, in classical glasses, this is known as East model, but it's a stochastic model. I mean, it's a stochastic model with Hamiltonian generator, right? It's a many-body stochastic matrix, and dynamical variables are just classical spins, right, which flip with some rates. So now this is no longer quantum mechanics, it's stochastic physics, right? But then you can think of time going imaginary, and then this becomes quantum Hamiltonian because generator is Hermitian, right? And then Juanpi and collaborators suggested that there could be transition when this parameter, which they call e to the minus s, goes from less than 1 to larger than 1. Yeah? And this has been known in classical East physics, and there it is called an activity-inactivity transition, because then this s corresponds to a tilting of Markov chain. This is only a stochastic matrix if s is equal to 0, but when s goes between less than to 0 and larger to 0, then this seems to undergo a transition, kind of inactivity-activity transition. And if you look at how eigenstates or ground state or steady state in this glass context changes when you go across the transition, you see it goes from localized to extended. Okay, I don't want to go into details of this classical East or quantum East, but Hamiltonian East, because this localization is not really a point of my talk, but it's just the background of the model. So if there is a question, of course, I'm happy to discuss it later. But this, of course, many people are interested in this kind of entanglement transitions. I mean, this volume law, area law transition. So this is supposedly an example, but one has to state immediately, I mean, there is no proofs. I mean, these are just numerics, right? I mean, the last paper I know was this PRX from the group of Marie-Carmen Banuls, where they used state-of-the-art tensor networks to simulate ground states and of this model, and they found, or eigenstates of this model, and they found this kind of nice phase diagram where you go from area law to, I mean, this is just the distribution of entanglement entropies of eigenstates, and you see you go from to volume law, from something that is mix of area and volume to volume law. Anyway, so I try to convince you that this model is much more interesting if one allows for Trotterization, if one allows additional parameter, which is the time step. And then it becomes a circuit, as I explained. And now we'll try to analyze, ergodic, or first localizing or localization properties of dynamics of this circuit. So now let's just if you think you can imagine it. I mean, of course, I already defined it for you, but you can now redefine it as a Trotterization of the quantum East Hamiltonian, if you want, with a left boundary condition. Now you assume that the leftmost spin has been in state 1. This state 1 is not touched anymore. It cannot change because it's just a spectator. Nothing to the left of it is excited. So this state 1 remains in state, let's say spin 0, it plays 0 is in state 1. Then you can remove it from the game, and then you can only describe spins in sites 1, 2, 3, and so on, right? So like I explained here, right? I mean, this everything to the left of this excited spin, it's kind of static, and all the dynamics is happening to the right of it, to the east of it. Okay, and then there you can describe this as if you want, as a brickwork circuit. right, in the even and odd layers of gates, right, in the standard way, right? Even layers is just tensor product of 2-qubit gates. Odd layer is just the shifted tensor product when you have a single qubit gate on the most left qubit. And well, I mean, I already told you that I prefer ladder formulation, but you might, disagree with that. You may say, okay, I like it. I like brickwork more. It looks more elegant, whatever. It is easier to simulate on a quantum device because it's just two cycles and so on and so forth. So yes, of course, I agree with that. But I want to convince you first that this is completely equivalent, and I prefer the ladder just because of conceptual simplicity. So. So this is my now explicit spelling up of the ladder circuit. And yes, and I mean, this is something I already used before, but now I write it explicitly. So if you apply it to a 0-0 state, to a vacuum state, you get back a vacuum state. So it's a special gate which preserves a vacuum, right? It's not a gate which has a U1 symmetry. It doesn't have a, this is also true for gates which have U1 symmetry, of course, because then 0-0 is the highest weight state. But this is not a gate which has any additional simple symmetries, but 0-0 is a ground state. I mean, it's a vacuum state. So it's kind of nice because then all zeros are stable, and then you make excitation somewhere, and then this excitation now spreads locally because the gates are local, right? So it has this kind of causal nature of dynamics, which is also true when people study operator spreading, right? So I also like to think of it. I mean, if you would like to have a simple model of operator spreading, then I claim, okay, this is maybe even simpler model than your favorite random quantum circuit, right? Because there you have 4 states per site, you have 4 Paulis. Here you have just 2 states, two operators per site, right? If you want. And how things go, right? I mean, now you have an excitation, and then things go, but of course they go only to the right. And okay, so now how we will measure this localization or dynamics or dynamical localization? We'll measure it by computing what I call partial norms. So we'll take a state which we start from 0-0-0, and then we apply dynamics on it, and then we overlap it with strings of spins where the rightmost excitation is at place x. Okay, and then to the left of it there is an arbitrary string. Okay, and then we sum over all possibilities. So the only constraint is that the rightmost spin is at place x. Rightmost excitation is at place x. Okay, so now clearly, if you sum over x, of course, this is done summed over Sj for j less than x. Now, if you sum in addition and sum over x, then this is 1 because it's just normalization of the wave function, right? And it's also true because of locality of dynamics that for fixed t, these partial norms are non-zero only for x from 0 to t. Okay, so you have some sort of hydrodynamics, right? You have some sort of density which can spread, right? Again, similar than in operator spreading. You have a density, a profile of operator, now in this case a state, which can spread. And now we want to understand, how does it spread? I mean, does it localize? Does it stop spreading? Does it freeze? Or does it continue spreading like a wavefront and never stops? And so now these kind of questions we can try to address, and we have addressed in this PRL I mentioned in the first slides. But before going into that, let me just convince you that brickwork is indeed mathematically equivalent to a ladder. I mean, this is just kind of identification of these diagrams, right? If you look at this triangle is equal to itself, but now you can cut out this small triangle like that or like that. So, and if you look at this tensor network identity, this is just intertwining brickwork propagator with a ladder propagator using this smaller triangular intertwiner, right? So it's clearly just a conjugation of the two propagators, right? And this small triangle is invertible, so it's a kind of really invertible symmetry between the two. Okay, right. So now I mean, of course, I cannot do, as I already told you in the beginning, I mean, so far still we cannot do much in terms of closed form analytics. Maybe it's not possible to do anything after all, but what we can do quite well, not really sophisticated, but quite detailed, let's say, perturbation theory. So let's first identify a small parameter. So first, let's take this flip amplitude A as a small parameter. And let's try to see if we can understand what happens at small a, right? And this is, of course, a simple textbook example of many-body perturbation theory and time-dependent many-body perturbation theory. So I will not go through details because it's really something that you can, I mean, it's like on a level of graduate course, I guess. But at the end of the day, what you get is this partial norm. You can write a partial norm in the leading order of A. So now the question is, I mean, what is the leading order in A? A is a small parameter, right? So now you want to know, I mean, I want to flip a spin at site X, right? X after time T, right? So now this is a high order process because I have to flip all the spins before that, right? So I have to, this is at least order X process. Now, if you square it, of course, this is amplitude. Now you square it, so it's A to the 2x, right? So this amplitude is at least of order A to the 2x times a combinatorial prefactor, right? So amplitude is A to the x, but the probability is A to the 2x times some combinatorial prefactor, right? Now, okay, I forgot also about the Trotter time, so it's A times Trotter time. Okay, this is the combination of A times tau is a small parameter. Fine, but Trotter time for me will always be of order 1. Okay, so right. So now the interesting thing is in this combinatorial parameter, right? So now, I mean, it's a standard issue of many-body perturbation theory. We have something that decays in small parameter. If it's a small parameter, of course, if there is a small parameter, but then there is a combinatorial factor which can win because there are factorials there and things can blow up, right? So now the question is, what does this combinatorial factor do? And here, of course, Trotter time, I mean, the commensurability or incommensurability of Trotter time can save us, right? So again, I mean, something that we can work out. I will not do it, but it's easy to do it. Is this expression, which is just a time-ordered sum. It's a it's again, like you do the standard, Born expansion, and then what you get is a time-ordered products. I mean, each term in the perturbation theory is a time-ordered. It's an integral or a multiple sum of time-ordered products, right? And here you work it out, and you find that it's just this. It's super simple, right? It's just this, but you see, this is just, what is it? I mean, this is, of course, satisfies simple recurrence. And if you try to solve this recurrence, it looks like binomial symbol with one crucial difference is that you don't add up once, you don't just count, but you also have phases. And these phases means that you have to compute not a binomial symbol, but what people call Q binomial symbol at unimodular values of Q. So Q is e to the I tau, and then this K is just this. Well, but that's nice, right? I mean, now people understand a lot about the behavior of these binomial symbols. For example, if Q is unimodular, these things cannot blow up. If Q is 1, these things blow up as factorials. So things will, not converge. But if Q is incommensurate with pi, so now the key difference is whether, I mean, this will be my next slide, so I don't want to overtake myself, but you see, I mean, this is now a simple expression. It's almost, I mean, it's almost too simple to be too good to be true, right? I mean, but of course, the caveat is just a leading order of perturbation theory. So then there's no reason why the leading order should describe what's going on, but already the leading order is interesting enough. So now we have some sort of transition, depending on whether tau is of the form 2 pi times a rational, or whether tau is incommensurate with respect to 2 pi. Okay, if it's 2 pi times a rational, then this, what I've said earlier, is not true. I mean, this binomial symbol still behaves like undeformed binomial symbol because, you know, we have a root of unity deformation, and things can and still will blow up as factorials, and you will get you will get partial norms with drift with a constant speed. Again, I've saved you with some derivations, but they are very elementary. What you get is that there is a wavefront. I will show you later some numerics. There is a wavefront which goes away with a constant speed. But if tau is incommensurate with 2 pi, then you use a simple kind of ergodic theory lemma or theorem, if you want, which is the statement that the shift on the rigid shift on a circle by incommensurate angles is an ergodic process. This is the only statement you use, and this statement is rigorous, and this allows you to bound this Q binomial symbol by a constant in time, which means that these things cannot blow up, which means that leading order perturbation theory will tell you that you are localized. Okay, now some numerics. Indeed, this is what's going on. So this is for small flip parameter, not so small, but still smaller than 1 flip parameter. You find that, and what I show here is the partial norm for different times. in time steps of 10 from 20 to 120, or time steps of 20 from 20 to 120, you see that basically you are frozen. These full curves are TEBD numerics. And then these points are exact leading order perturbation theory. And this is working very well for irrational tau. But if tau is rational, which is in this case is 2 pi over 3, then you see that the perturbation theory no longer works. This perturbation theory is completely off. And not only that, I mean, the process is not frozen anymore, but these partial norm profiles start to build up, right? And this in the insets you see also through this dynamics of entanglement entropies. You look at entanglement entropy of a cut at place X, and you see how it goes with time as a function of time and X. You see here it's just kind of super small, and it's just swinging up and down around super small values. But here it starts to systematically blow up, even though it's still small entanglement entropies, but it blows up systematically. So it shows that, you know, even though the flip amplitude is small, so perturbation theory might still be okay, but the fact that you have irrational tau means that you have combinatorics that beats you. Now, if you are at much higher value of flip parameter, then you get what I described earlier as this wavefront of either entanglement or partial norms, which moves to the right with a constant speed, which we can estimate analytically. Again, I didn't compare this with analytics in the figure, but we checked it in terms of numbers, and it fits very well. Okay, now let's change gears a bit, and now let's go. Okay, so first, let's go now. So far, I discussed something that is maybe easy to analyze using perturbation theory or TDABD for small a, but it's maybe not so easy to simulate in terms of, let's say, real-world experiment or quantum simulation device. Let's now look at something much maybe more easy to measure, which is local observable. So now let's just look at local observable. Let's measure z as z at place x at time t, right? Starting from state 0, 0, 0. So this is a kind of correlation function. I mean, if you want, it's an observable, local observable after a quench, and morally it's like having a correlation function, 2-point correlation function. And again, here I'm just showing how it behaves as a function of time for different axes. So this is leftmost side, next to leftmost side, and so on. And this is the rightmost side. Okay, so now I take an east model of L sides, right? And I take different L to 24, 30. And what we see is that basically first leftmost side or near leftmost sides behave. I mean, now I'm just looking at what remains at the left, right? What remains at the left, I mean, like an edge mode, right? I mean, this is like a theory with a boundary. Now the question is, how does this, is there some evidence that there is an edge mode, which means that correlations at the left boundary will not decay? And again, this is something that kind of shows a nice kind of transition that goes from, I mean, when A is small, it seems that there is, kind of localization, which also would signal an edge mode. And when A is large enough, for example, when it's order 1 or 2, then this starts to decay exponentially. So this is a correlation function which has a clean exponential decay. And also it seems that, after a very long time, up to quite a long time, things don't depend really on system size, but only after they become exponentially small. There are tails which are exponentially small as well because of finiteness of Hilbert space when things start to quasi-oscillate, right? So, and of course, this is comparing 24 and 30, you see that basically I just decrease a bit, by 2 to the, I mean, the value at which you fluctuate, you can estimate it's order 2 to the minus L. So yeah, but before that, you basically have a very clean, nice exponential decay. So the rest of my talk now will be to describe these exponential decays. I mean, I'll try to maybe discuss some earlier work when I looked many years ago, but now people also look at 2-point functions in translation variant models. And here I want to claim, okay, I mean, I just refer to that, but here I discuss something simpler, which is non-translation variant model is a model with one boundary because it's chiral. Everything moves to the right, so it has just one boundary to the right. We just, as you will see, we'll make some sort of absorbing boundary condition, but we are interested in the left boundary, and we're interested in correlations of something that's localized in the left boundary. And before, I don't I hope I don't get too technical, but if you lose me because of you feel it's too technical, I just want to straight away stress that I mean that these two things are very similar. So from conceptual point of view, looking at decay modes localized at the boundary of a boundary theory might behave in a very similar way than looking at local translation variant observables of doubly infinite theory on doubly infinite lattice. I mean, also technically, like how you construct the transfer matrices, which describe this decay, they look very similar. So I will come back to that, but you know, it might sound more technical later, so I just spelled it right away. Okay, so now let me try to discuss the main.
Sorry, Thomas, I had a question about the previous. So if you look at the same expectation value in some slightly excited state, do you also see localization, or does it immediately not look localized?
If you start from some more excited state.
Like if you look at the expectation value instead of all zeros in some excited state.
Right. I mean, I think what's important is that there is an extensive number of zeros, so that there is excitation which is local, right? So only at the finitely many sites near the left end, right? And everything else to the right should be in zero. I mean, if you want to ask what happens if I take a null state, then I don't know. I have no idea.
Okay. So I look at some.
Yeah, sorry. This mimics like an infinite temperature state, right? Because of what I said earlier.
Okay.
Okay. Okay, so now let me try to, but now I shift gears. Now I go to defining really infinite temperature in a standard sense simulation. So now I define a Markov chain, right? So I mean, as I said earlier, I mean, things go to the right and well, presumably never come back. But if I have a finite system, still, I mean, things affect, I mean, finiteness of the system. You will get, I mean, local correlations will be affected by finiteness of the system, of course. And the question is how you can reduce this effect of finite system to a largest possible extent. And of course, the idea is to make some sort of absorbing boundary conditions on the right. And this I will do in terms of writing a quantum Markov chain. So defining a kind of Krauss map, which has some sort of forgetting channel on the right. This forgetting channel is technically referred to as a reset channel. So I'll just, I mean, you might want to do another, you may want to do some other channel, you know, some dephasing or depolarizing channel. But it turns out actually that for the East model, it does not really matter, right? Because of the nature of the East gate, which pushes things to the right, it does not really matter what you do on the right. You get a state, you get a process which has a fixed point, which is completely mixed state, right? Which is infinite temperature state. So this will be discussed in the next slide. Sorry, I'm still overtaking myself a bit. Okay, so now let me just try to discuss what I mean now. So what I will define now is a Markov chain, which is defined on L+1 sites. So let me imagine I have additional site L+1, which I will then couple. I mean, this is an L+1 site, which I will then put to state 0, 0, and then trace over it. Okay, this is the way you can imagine constructing a Krauss operator for the reset channel. Okay, so now if you want diagrammatically, I will use some diagrammatics also later. So in diagrammatically now I will, first of all, I mean, I will do now the thermophile double or vectorized or whatever you want to call it to replica picture, right? So I will now introduce dynamics on the space of density operators, right? I will introduce now a unitary or subunitary dynamics on a space of density operators. So I take a density operator as a state. So I'll fold these two gates together. Then I'll just fuse these two wires into a single wire. And then I paint the gate as a green circle, and green circle for me will be already thermophile doubled gate, right? Acting on these joint wires, okay? And then I will also introduce this process, which I just described, the right boundary process, which will be this box, right? Which I will denote as this box, which will be the reset gate, the action of the reset gate, combined with the one layer, with the one gate on the two boundary qubits. So at the end of the day, what I have is this. So I have reset, then I have a reset on the first. I have reset, right? Time goes from bottom up. First I have reset, then I have this folded gates folded east gates, and then at the end I have the let's say a folded single qubit gate, which is just a green box, a green ball. So this will be what I call W, and this will be my quantum channel. So many-body quantum channel. And the rest of my talk is to try and understand the asymptotic properties of dynamics of this quantum channel. So I feel I don't have really good, well, as you see, I have good numerical evidence, but I don't have any analytical evidence yet that this is a very interesting channel, that it has potentially a transition and maybe even has some way to describe asymptotics of decay of decay, and also some asymptotics of the eigenstate, which indicates the decay, as you will see. Okay, and as I already kind of tried to announce, but I didn't have the slide yet. So this channel has, even though I put the so-called reset channel, which reset channel wants to target the last qubit into down state or 0 state, right? So it's not at all infinite temperature, right? It's the opposite. It's a 0 temperature. But because of the nature of this gate, the claim is that even that channel heats up to infinite temperature. That means that infinite temperature state, which is this bullet for me now is the vectorized identity. So the string of bullets, this tensor product of bullets is a fixed point of the channel. So it's a trivial fixed point of eigenvalue 1. And moreover, I claim this is the unique fixed point. So this is the unique steady state. It's a trivial steady state, and it's unique. So nothing interesting about the asymptotics, ultimate steady state. What we are after now is the decay rate and the nature of decay towards a steady state. Okay, now let's see if we have learned anything. Even if you cannot do anything analytically around this channel, I claim it's still useful to use this channel to describe, let's say, local correlations on the left hand, because you can work with much smaller systems. Of course, you say, yes, but you have to double the space, so it's just, a factor of 2. Yeah, but still, look, for example, now I compare closed form numerics for L equal 24 and 30 with open system numerics for L equal 12 and 16. Well, even 12, you see, describes extremely well dynamics at short times, not so short times, but even up to time equals 60. But then it continues to decay exponentially, right? So now, again, I compute this boundary correlation function, boundary quench observable, boundary magnetization, if you want, as a function of time, using a quantum channel compared to closed system, which is unitary without dissipation. And yeah, you see that there is a very good agreement, but I would say, yeah, using this absorbing boundary is much cheaper, even for doing pure numerics. And then, of course, the question is, do we still see a transition? Now a transition is a bit different because now this is transition at infinite temperature in terms of local correlations at infinite temperature, but still, is there a transition, thermalizing, non-thermalizing transition? For example, here I plot now correlation functions at left hand, near to left hand, and on the right hand for different values of the flip parameter A, going from 0.2, I don't know, it should be the same values. But anyway, it's not so important. They go from 0.2 to 2.0, I think. And they start to, as you will see later, they start to bend around A equal to 1. So, for example, you can write some sort of phase diagram where you look at the right boundary steady state value. So you take now the right boundary and you look at the value of the right let's say at the maximum time of simulation. So you take this maximum time of simulation and then you plot it as a function of the split parameter A, and you get this kind of sharp transition. Yeah. Now this transition seems to be okay. It's not completely frozen in terms of system size, so it's not really clear what's going on. But yeah, it might be that there is a kind of discontinuous transition that between, let's say, thermalizing and ordered phase. Okay, right. So now I think I don't want to get too many things. So maybe I skip a bit. I just go very quickly through this, but one can do also.
Excuse me, Tomaz, sorry. I ask a clarification question. So in the previous slide, what if you take the next side, like not the sink, but the side close next to the sink?
I don't think that it matters very much because yes, I think I don't show it here, but I think it's just shifted a bit. It just shifted by 1 here. It starts to, yeah. I to be honest, I haven't checked that, but I don't expect anything dramatic. I mean, I think that's.
So does that mean this kind of phase transition is actually detectable everywhere in the system?
Yes, I think so.
Okay. Thanks.
I just decided to use the last spin because it seems to be the most sensitive, but it's I think it's detectable even if you look at the first spin, the leftmost spin, you see that. I mean, for example, another order parameter would be just to look at the correlation decay, right? And correlation decay actually is the rate is the same for any spin if you wait long enough. And if you decrease A, then it becomes longer. I mean, the time scale becomes longer and longer. So the inverse time, the rate of decay becomes smaller and smaller. So I expect that if there is a transition at the transition point, this decay rate will go to 0. I mean, yeah, it will stop decaying. Okay, and then the similar story happens for the 2D, but 2D is kind of much harder to simulate. So, I mean, for example, what I can do is 5 by 5, and then I put resets, these reset channels on the eastern and northern border. And then I have to put still some excitation on the southwestern corner. And well, then you can do the same game. You find that depending on the value of A, this is the leftmost spin, I think. I mean, this is the corner. Well, I don't know. Yeah, it's written there. I just forgot. Yeah, this is the southwest corner, and this is the towards northeast. And you find, yeah. Yeah, this is for different A, right? This is for, well, presumably there is again some sort of transition, and then A goes from where A goes from 0.4, where it seems to be localized, well, to 2.0, where it seems to be kind of thermalizing. Anyway, now if you look at what happens, 1D versus 2D, you see that 2D seems, of course, more sensitive to this. And of course, I mean, you might expect, and probably everybody would expect that in 2D things tend to be ergodic no matter what. So there's a question, what happens to the thermodynamic limit? And there's all hard questions. So yeah, but anyway, I mean, this numeric seems kind of intriguing. But now let's go back to 1D where things are much clearer. And let's now try to get to the main point of my talk. Let's try to see if I can interpret this as a quantum Ruelle-Pollicott resonances. I mean, let me go back to a bit. I mean, I should have probably gave you a bit more of introduction into this concept of Ruelle-Pollicott resonances, even though, as I said, I mean, in classical mathematics of dynamical systems, this concept is very technical and uses completely different mathematics, which we cannot use in many-body quantum physics. But still, I mean, intuitively, it's kind of easy to explain, right? I mean, the idea is basically to do some sort of coarse graining, right? I mean, you define dynamics in the space of observables or in phase space, and classically in phase space. In quantum mechanics, instead of phase space, you use some algebra of observables, and then you truncate this algebra, meaning that you don't care about observables which get too wiggly, too complicated, or you don't care about phase space densities which get details on too smaller scale in phase space. So the idea is to define some sort of coarse graining parameter, and you truncate. Or in other words, you can define a sort of noise, external noise, and then you take the limit of noise going to 0. So these are the two approaches that people use in classical systems. They either do coarse graining in phase space, meaning, I don't know, you do Fourier and then you cut out some Fourier modes with very small wavelength, very large K, or you do some small noise, some small white noise, and then you take noiseless limit at the end of calculation. And what people observe is that the decay rate of correlations sometimes freeze. They are not sensitive to the truncation parameter. So there exists a limit of noiseless system or which has a well-defined mathematical properties. I mean, this is easy to describe in words, but it seems, as I already said, it's very hard to make rigorous mathematics out of it. And people are still, I mean, I checked a bit recently, I again checked a bit literature, and I still see that people write papers in mathematics literature around very simple problems, right? Single particle problems. So there are still issues, right? I mean, as far as I remember from studying this many years ago, I mean, It was not clear, and the main problem was how to appropriately define a function space. I mean, you have to define appropriate function space to treat these transfer operators over densities in phase space, and this depends on a class of systems. I mean, the function space you have to use, and so this is not very nice. But well, in any case, I don't want to go further into that. But it's now we are in many-body quantum physics. The question is what you have to do there. And this proposal, which I had many years ago, said the following. I mean, let's just consider Heisenberg evolution of operators, right? Local operators. Let's consider translation variant operators. And once they spread too much, so your operators have grow, right? I mean, they require longer and longer Pauli strings. But then you just describe a parameter, let's say R. And if the Pauli string grows over R, then you just cut out this operator, right? Actually, that's very similar to, I mean, now there has been some idea. I think there was an idea by Kurt von Kaiserlink and Frank Polman and Tibor Rakowski. They call it DAOE or something. I mean, it's a hard to pronounce acronym, but the idea is quite similar, right? I mean, even though they looked at k-locality operators, not contingent strings of Paulis, but still they kind of cut out the operators which gets to non-local, right? But they cut them out with exponential weight, right? So that e to the minus something which depends, I mean, e to the minus constant times the length of the operator. So the longer the operator, the more you damp it, right? But morally it's very similar, okay? And morally, I think that idea is a kind of way of thinking of Ruelle-Pollicott resonances. I mean, so yeah, going back. So now, I mean, what I defined there, right, was just an operator, a transfer operator, which defines Heisenberg evolution of operators in Pauli basis, composed with a projection which cuts out everything that grows too much, which grows over R, right? So then you get then you get a matrix, right? You get a finite matrix, which maps an operator, which is a superposition of Pauli strings of length from 0 to R, back to itself, back to the same space, right? It's a finite space. Then you can diagonalize it and you look at the spectrum. The spectrum looks kind of nice. It looks like a spectrum of a quantum channel. It has a leading eigenvalue. Of course, you take out the trivial leading eigenvalue, which corresponds to unit eigenvector. This is completely separate from the rest of the story. Then the sub-leading eigenvalue is this one, which is here indicated by an arrow. This is a picture from the old paper, which is for the Kick-Teasing model. And there you see that depending on the parameters of the model, then you find that this leading eigenvalue either freezes. It's independent of the way where you cut. So it's independent of the strength of the noise, if you want, or of the truncation parameter or the coarse graining parameter. And this is in the ergodic phase. I mean, this is the longitudinal field. There is a transverse field, and then there is a longitudinal field. And if there is a longitudinal field, the model is chaotic, so that the gap is frozen. And these two halves of the circle are two subspectra for two different parities. And operators can have positive or negative spatial parity. So for the two subspaces, you get different gaps. So the two correlation functions can decay with different asymptotic exponents. But this gap seems to be insensitive to the length of the operator. So they seem to be kind of well defined. And okay, that was the proposal. And that proposal, of course, can also be used to target integrable, so quasi-integrable systems, right? When this gap closes, for example, when you take longitudinal field, sorry, this is transverse field, sorry. It's longitudinal transfer, such that when it's 0, it's longitudinal field, yes. So when longitudinal field is 0, this is non-trivially integrable situation, where you have then many eigenvectors or eigenoperators of eigenvalue 1, which correspond to local constants of motion, local operators which are conserved under dynamics, right? And in this way, you can also find not only local, but also quasi-local or pseudo-local operators. For example, when you have a theory which is quasi-integrable, or for whatever reason you are targeting operators which are not local, but still you know that they should exist, they will be appearing as the eigenvectors of eigenvalue which approaches 1 when R increases. And if the eigenvector, if the eigenvalue only approaches 1, it's not exactly 1 when the R increases, meaning that the operator gets more and more, local. There is more and more weight of an operator within Pauli strings of size R. So which means that your eigenvalue will go to 1, right? So, I mean, from that convergence of the eigenvalue to 1 or non-convergence or gaplessness, you can then decide whether operator is quasi-local or is just a decay mode, is just a Royal resonance. Okay, now I mentioned there was recently a revival of this concept. In particular, the first was this paper by Takashi Mori. I just want to comment that there are many other ideas of how to truncate operators, right? And what Takashi Mori proposed was to consider simply a Lindblad equation. I mean, Lindblad equation with local, with the local dissipation channels, which will then, and then he took the strength of coupling to the Lindblad to 0 at the end, and he claimed that he found situations where, again, the decay rate was insensitive to the strength of the Lindblad coupling in the thermodynamic limit. But again, the question is, there you have to take thermodynamic limit before you take 0 coupling limit. I mean, it's delicate, and well, I mean, we've been discussing this with Marko Žnidarić and his student recently, and I think, I mean, we claim that this method is much more robust than the Lindblad coupling, because that Lindblad coupling seems to depend a lot on the structure of the Lindblad channels, which are not so easy to motivate from physics. But anyway, I think, well, I don't know how much time we would have. Should I finish with everything in 1 hour, or do I still have like 5 minutes?
No, so it was actually 50 minutes plus 10 minutes of questions. So maybe if we could wrap up in a couple of minutes. Okay,
thanks. Because now I want to discuss the kind of the main part of my results, which is the, let's say, the unpublished part, which is interpreting the eigenmodes of this W, the quantum Markov chain that I defined for the East circuit, as a Ruelle-Pollicott resonances. So this is slightly different because now the operators are sitting near the left boundary, so I don't have to translationally shift them, right? I don't have to make them translation invariant. They already automatically, if they are local, meaning now I will just truncate. So let's go back to the definition of this circuit, right? I'm taking this circuit now. This is the absorbing boundary, and this absorbing boundary now is a caricature of noise, right? It's my noise, but it's only the longest operator, right? Now imagine you have an operator which is glued to the left end, and then it grows. And it only gets cut away when it grows too much, right? Because otherwise, if its identity on this last side, it's just invariant under this, right? So it's not hurt, right? It only gets hurt when it becomes non-trivial on the last side, when it gets contributions with non-trivial Paulis on the last side, then it gets damped, right? Then this terms gets erased, right? So I mean, intuitively, it's a very similar picture as I explained earlier in this Kick-Teasing chain, but now it's even simpler because we don't have to care about translation invariance. We just have something that is glued on the left boundary and gets absorbed when it grows too much. Yeah? And okay, and now I'll just define that there is this one technical slide, which maybe is too busy, but it's just, I mean, bear with me maybe for 2 minutes with it. And then I'll show you some nice pictures. Okay, so now, I mean, what we are doing now is take a system of size L, and for us, this is not a finite system. For us, this is finite operators, because we put absorbing channel on the L plus first side. So basically, we should imagine rather that we take a semi-infinite lattice. We take an East model or chiral circuit on a semi-infinite lattice, and we just truncate it to finite observables of length maximally L. So we take an operator which is supported on Pauli strings of size up to L, right? So we can just imagine there's a Pauli strings of size L with Pauli digits which are 0, 1, 2, 3, 4. 0, 1, 2, 3. And and then we just define a length of the operator as the rightmost non-trivial digit. Yeah? So we can order these digits from least important on the left and most important on the right. So it's just the reverse Arabic convention, right? Okay. Fine. So now I will define these eigenvectors as the expansion coefficients in the Pauli basis, right? Right, and now I can define the spectral decomposition of my matrix. The spectral decomposition is the eigenvalue times the right eigenvector times the left eigenvector. I assume without loss of, well, I mean, I don't think it's relevant now to discuss the Jordan block cases. So let's assume there is no degeneracy and that there is no non-trivial Jordan block structure. So let's assume that this guy can be diagonalized. But of course, it's a not normal matrix. So the right eigenvectors and the left eigenvectors, these are the decay modes, the density operators, so to speak, and these are the dual decay modes or the Heisenberg operators, if you want. But of course, from the basic feature of linear algebra, these two guys are biorthogonal, right? So you can define this Hilbert-Schmidt inner product, and by construction, they are biorthogonal. I mean, you can define them as biorthonormal. And right, and now let's define lambda 0 as the leading eigenvalue, which is always there, corresponding to a leading eigenoperator, which is the identity. So then lambda 1 will be the subleading eigenvalue, okay? And right, and okay, and then if you define, for example, and then what we'll be looking at, of course, now this is completely general, but we'll be looking at this boundary, this single site operator, starting from the initial state, which is ground state, right? So ground state just means we take one operator, we apply this Markov chain on it, and then we project it to let's say local operator. This is not local, doesn't matter, because we project it to the leading. I mean, we are now looking at the leading asymptotic dynamics, right? The asymptotic decay, right? Of this quench observable, right? So now we have coefficients and we have the rate, the dynamics, right? The temporal behavior, right? So for example, this will be dominated by the lambda 1. So we have to compute also C1, right? But what is C1 or Cn? The C1 or Cn, I mean, for our case now, this is just this component for this particular Pauli string, because this is our Pauli code for the Z operator, Zx, right? It's just 3 times 4 to the x minus 1, right? So this is just the appropriate component. It's appropriate projection of Zx on the left eigenvector, on the right eigenvector. And then we have to also project initial state on the Heisenberg eigenvector, on the left eigenvector, right? And then we get the coefficient. Okay, so we have a explicit expression for the coefficient and for the eigenvalues, and for the dynamics, for the time dependence, which is to the eigenvalues. Okay, so now, yeah, this is very elementary linear algebra, of course, but I now claim, okay, even without further results.
Tomaz, if you could wrap up in maybe a couple, like 1 more minute, that would be great.
Okay, good. So I'm almost done. Yeah. So I just want to show you some nice pictures because I want to motivate with pictures. And I have not much intelligent to say anymore. But so for example, this is how the spectrum looks like for 2 different cases, where A is 0.6, where there seems to be still no gap. This was before this higher temperature transition, if you may remember, right? The transition was around 1. And for A equal 2, then there is a clear gap. And this arrow denotes fixed position. So now this is compared 5 to 6. You see that position doesn't really change. Now, if you look at how the gap goes for L, this should be capital L, from 4 to 16, you see that it has very nice convergence, right? And at the end, it's kind of almost flat. And then we can easily extrapolate it to infinite size. It seems there is a finite gap of order 0.1. For this specific case. Now, how you want to characterize locality of this decay mode? I mean, this decay mode, you may wonder whether it has anything, whether it's local or not, because it does not correspond to. I mean, now I don't have time to go into that, but one can convince himself that if this operator in the Pauli string basis would be localized, would have kind of convergent L2 expansion, right? Then this would imply that his eigenvalue has to be in unit circle, or vice versa. If eigenvalue is within unit circle, within unit disk, then the sum of rho square or sum of chi square has to diverge. So it cannot be normalized. But what will be normalized by the definition is the byproduct, is the product of left times right eigenvector. So what I plot here is what I call binorms. You can split this byproduct into strings of given length. And you can now see how these binorms, which are kind of miraculously positive numbers, they don't have to be, these binorms add to 1 and they decay exponentially. Okay, that's an observation. I have no explanation for that, but that's very nice, right? They decay exponentially, which means this all makes sense, right? This is, again, different system sizes from, I don't know, 8 to 16. Now, okay, so I have to wrap up. So what I think, well, I had this, but I didn't, no, I didn't have it. Okay, so what I really kind of find cool, but I really I'm not yet able to explain anything, but what I really find cool is this kind of self-similar fractal structure of these eigenvectors corresponding to the leading eigenvalue. For example, if you take this density operator, you define all its components, and then you build what you may think of as a super operator, as a super density matrix. So you think of this as a vector, and then you build super density matrix out of it, right? Then you can, and then you order, I mean, you order these integers, right? Again, the way I explained, least important bit is on the left, most important bit is on the right, or digit is on the right. So then you average over least important digits, right? You average over R least important digits. It's like tracing out, but now it's tracing out in superspace. You trace out R least important bits, and then you define some sort of reduced super density matrix. And what you find is this reduced super density matrix becomes self-similar. Actually, it's the kind of RG fixed point, right? It becomes a rigorous RG, well, rigorous. I mean, it becomes a kind of RG fixed point once R is large enough. And then there is some coefficients, right? Some scaling exponent, which you may call mu and mu prime. And from the numerics, it looks like 1.3 and 1.1, depending on the left and the right eigenvector. And I just want to convince you that this, what I've described, very much makes sense. For example, here I just plot the diagonal of this super density matrix corresponding to leading eigenvector. I plot it as a function of R for different R, 8, 9, 10, and the curves basically sit on, and of course I scale with the R, mu to the R, and then these curves just sit on top of each other, which is, I mean, I find it quite non-trivial, right? And this is for the right and for the left eigenvector, which have different scaling exponents. And this you can do in 2D as well. I mean, you can do it as a function of row and column indices, right? First, before I show the diagonal, now I show you the 2D plot. Again, this is R8, 9, 10. And you see that pictures, I mean, if you inspect them by your eye for 2 minutes, it's one of these games for children, right? Can you find differences between left and right picture? I mean, of course, you find little differences, but gross pictures are really the same. Okay, so I think I'm done. So I will just leave the conclusions on the screen, and I'm happy to take any questions if there's still time.
Tomaz, it's Xiaoliang again. So what is there any system where we know the real resonance analytically? Quantum system.
Quantum systems, I don't know. Actually, we are actually thinking of dual, to discuss this in dual unitary circuits. In dual unitary circuits, I think, yes, they can be described exactly, but they're kind of trivial. I mean, in dual unitary circuits, I believe that they can be described exactly, but yeah, okay, I mean, I don't want to get too technical with the answer, but I mean, the short answer is I think the dual unitary circuits, they can be described exactly, but it's still not done, and we are thinking about this.
Okay, thanks.
Oh.
Hi, you mentioned that you thought that this truncation of operators based on range kind of worked better for identifying these resonances than Takashi Mori's technique of introducing noise. Could you comment a bit more on that? Exactly what works better, and why do you think that that's the case?
No, I mean, I don't know. I don't really understand much. We were just playing a bit with, Marco's student, actually, Urban Duch, he's playing with different models of noise. And what he finds that it's different Lindbladian noise, and things seem to be quite sensitive. Unlike here, when you take this Pauli truncation, seems to be much more robust, but that's just experience. So we don't understand anything yet. So
okay, thanks.
Hi, Thomas. This is Luca. So I wanted to ask you. You motivated these row resonances by saying that exponential decay was pretty ubiquitous. On the other hand, it's not generic in systems with conservation laws, like say energy conservation. I realize actually now that you have a paragraph on this. Maybe that answers my question. Yeah. So I guess the question is, so they're right. Presumably, this kind of are resonances still interesting in this context? I guess you get polluted, right, by all these very slow resonances. Is there still something interesting?
Yes. I mean, there is a whole section in Takashi Mori's paper on that, because I think I mean, yeah, I mean, one can try to project out this trivially conserved, well, I mean, operators which are related to trivially conserved, trivially, I mean, conserved quantities. And then, so yeah, you expect that, for example, when you have U1 symmetry, you expect that you will have no gap. So there will be hydrodynamic modes, right? But you may still find exponential decay of some observables which are kind of orthogonal to these hydrodynamic modes.
Yeah, this I expect is actually impossible generically, because you'll have, higher fluctuations of hydrodynamic modes. I think it's probably a losing battle.
Okay, so it might be. I mean, to be honest, I'm not serious at all about this, but it's, I mean, one should reread what has been written by Takashi, but yeah, I mean, you might be right. I mean, sorry, I don't want to make strong claims here. I mean, so far I've always kind of avoided U1 symmetry. I mean, additional symmetries, but. So anyway, I mean, no, but there might still be something that's frozen in the, I mean, some resonances that, yeah, that are frozen. No. Yeah, okay. I mean, I'm not able to say anything deep at the moment on that.
Again.
Okay, thank you.
Yeah, maybe if you could unshare.